Hello everyone, welcome back. So today, let's firstly review what I have covered in the last video. So in the last video, I gave you a very simple example and I gave you a very small training data. And we want to use these 3 points to predict the price of the house. And we want to use this linear model, so it's linear regression. And our purpose was to minimize this loss function here. We want to minimize this loss function. And we define this loss function as the residual sum of squares, RSS, as in this form. So it's the difference between our prediction and the ground truth, and we take a square and we sum over all the data points here. And of course, you can also choose other loss function, such as this one. But this residual sum of squares loss function is more commonly used in linear regression problems. And because here we only have one feature, so in the weights, we only have this bias term and this W1. So we need to take derivative over omega 0 and omega 1 here. So we take the partial derivative and we set them to 0. And so then we can get the optimal weights, omega 0 and omega 1 here. And we found that by going through this calculation, eventually we can find our optimal weights as this vector. So sometimes you may say a notation like this. So omega star is our optimal weights we want to find. You may say the notation like arg, mean, omega, and RSS, omega. So this means that this arg means argument. And so here mean means minimum. So this means find an argument, omega, that can minimize this function, this loss function. So don't be confused by this notation here. It's just a notation. It is the notation. It is the omega that can minimize this RSS. So you may sometimes see this notation. So don't be confused by this. Okay. So here in this video, what I want to do here is I want to calculate a closed form solution for linear regression. So by saying a closed form solution, I mean that I want to find a solution to solve omega star. That is our weights, our optimal weights that can minimize the loss function. So in the last video, although we have obtained this omega star, but this is only based on a very simple example here, right? This is a very simple example. We have only one feature, and we can, of course, calculate this by hand here. But what if in our real practice, we have so many features and we have so many data? So it's nearly impossible to calculate this derivative by hand. So we need to ask our computer to calculate this for us. So we need to have some solution for this, for how to calculate the omega star here, and we ask our computer to calculate this. So here we will generalize this solution. We will generalize this solution and find the optimal weights here. Okay, so in this video, I will have some mathematical calculations, and for this one, it's all about some metrics and vector calculations. So if you forgot how to do some metrics and vector calculation, you can have a review on that, but no worries. Here the calculations will be simple, and it only requires the basic calculations here. Okay, let's get started here. Okay, last time we said in our linear regression problem, the loss function is the residual sum of squares RSS omega is equal to summation over all samples. We have n samples, and this is our weights multiplied with the feature vector and minus our ground truth, and we take a square. So this is our loss function we defined. So now we want to take this gradient with respect to omega, because we want to find this optimal omega, so we need to take the gradient to this omega. So you should pay attention that this omega here is a vector. It's not a number, it's a vector here with respect to RSS omega. Okay, so if you can see, if I want to take a derivative of this one over omega, so this is a composite function. So we will use the chain rule again here. So if we use the chain rule, so this is a square, we should take a derivative of this square first. So this one, it will goes to firstly like this. This 2 will goes to the front. Okay, the power now is just 1 here. And then we should then take a derivative of this one, right? So here I will just write it in this form. I write it like this because, you know, this is a vector, not just a number. So you cannot just write it in some form. So I just write it in this form like this. Okay, so I name it as equation 1. So here I will tell you an equation that you will use, and I will do a little proof here. Equation. So that's the derivative over a vector here. So this one. So I will tell you that this one, this omega transpose multiplied with xn, do a partial derivative over omega, it is equal to they are equal to xn directly. So if we have this equation, we know this one. So this one is nothing but xn. So we can have a little proof here. Why this y is right. Okay. So I will just prove this one. Okay, so we said they are all vectors. So if they are vectors, I take a partial derivative over omega, means that I take a partial derivative over the elements inside of omega. So here I will write like, okay, so you remember inside of omega, the elements starts from omega 0, and then we have omega 1 goes to omega d, because we have d features here. Okay, you can imagine what is inside of this. So here you should pay attention that, so this omega 0 is just, this one is a scalar, but these two are still vectors. So when these two vectors are multiplied together, and you take a partial derivative over omega 0, so here you will get 1, because this one will give you, okay, I can write it to here, because this one will give you omega 0 plus omega 1 x1 plus omega d xd, right? So you take a derivative of this one over omega 0, it's just 1. How about the second term? You take a partial derivative over omega 1, it is x1. So, and they are all the same, so it's x, well, this should be d, and xd. Oh, I should put a transpose here because they are column vectors. And then you will find that this vector is nothing but xn, right? So this is just the feature vector of the nth sample. So I have proved that this equation is right. Okay, let's get back to equation 1. Okay, so thus equation 1 will be equal to, okay, I just copy it here, to summation from 1 goes to capital N omega t xn minus yn n xn. Okay, and so this equation is equation 1 is after I take the partial derivative and I set it to 0, because we want to find the optimal weights. So we should set this gradient to 0. Okay, so now if this equation goes to 0, so this 2 doesn't matter. And here, you should also always pay attention to the notation here. So here, this one, xn, omega, are all vectors. On the other hand, this yn, so this yn is not vector. So this yn is a scalar. What is yn? So yn is the ground truth of the nth sample here. So after I done this, so we know that this one, we have said that omega t transpose multiplied with xn, it will equal to xn transpose multiplied with omega. So I will apply this equation, I will apply this property here. So this equation goes to, this is not changed, xn, I just put this xn to the front, and then I change it xn transpose multiplied with omega minus yn equals 0. So these two equations are the same. Okay, and then the next step is I will distribute this xn to to the bracket. So here is equals to 0 here. Okay, so because this omega is not connected with n, so I can put a bracket here. So you can see our optimization changed from this gradient to finally to this equation. Okay, so now I will do something like this. Okay, and I will name it just as equation 2 here. So next thing, I will define a very important matrix. I will define matrix X. So it's the matrix X of the is the I can put it in this way. Matrix X is the matrix of all of our tuning points. So this X, I can write it like this. So X1 transpose. So we know X1 is a column vector. When it is transposed, it will be a row vector here. It's the same X2 transpose. And because we have n data, so we have Xn transpose here. And if we expand it, so we will know that this one, because our first entry of the feature vector is just 1. And then the next one is X11. And then X12. So you now see why I put two subscript on the X, because so this first one means the first sample, and the second number means it's the second feature belongs to the first sample. So this may be confused here, and X1D here. And the second row is also the same. It is the feature vector belongs to the second sample. So this is X21, X22, X2D. Okay, I can put it. So the first number is the first data, and the D is the D feature. Because each data we have many features. Each house we have number of rooms, we have the area of the house, we have the distance. So this line represents one data, just one data. Okay. Hope you are not confused on this. And then 1, and of course it's the same in 1, in 2, and X and D. So you can see the dimension of this matrix. So let's see the dimension of this matrix. How many rows we have here? Because we have n data, so we have n rows. So the row is n, and how many columns we have? We have D, capital D features here, but we have another column that is all 1. So we have D plus 1 columns here. Okay, this is the X matrix X I defined. I also defined the vector Y. So here y is a vector. It equals to y1, y2. This is simple because we have n samples, we have n ground truths. So here. So the dimension of this vector is just n by 1. Okay, now you should convince yourself that we can write this equation 2 in the matrix form like this. Then we will write equation 2 in the following matrix form. So the form will be like this. So this equation 2, if I write it in a matrix form, it will be like x transpose x omega minus t y 0. So this equation 2 here, this equation 2 is same as this equation here. Okay, if you don't understand this part, no worries. Now I will prove it. I will prove why this one is the same as this one. Okay. So let's firstly. So here we have two terms. One is this one, another is this one. So let's firstly see what we can write this one. Okay, so this term I will just maybe so we can I will put it to here. Why they are the same? We can see that if we can prove that these two are the same, so this omega is not changed. So if we can prove these two terms in the red circle, and if we can prove these two are the same, we can prove everything. So now let's prove it. Okay. So now we can write this one first to see what it is. So this one, okay, and I will have this summation here. So we have said that xn is just the feature vector. So this feature vector is like this, 1, x. So the first number should be, okay, the first number should be the nth sample, and the second number should be the first feature. xn2, xn, because n is a variable, n is changed, and xn d. And what about its transpose? Its transpose is very easy. It's 1, xn1, xn2, and xnd. Okay, when you multiply these two vectors, you will get matrix. And the summation is the same. Okay, the matrix will be like this. So you use this. So it's a simple matrix calculation. So the first row is 1, xn1, xn2, xnd. And the second row is xn1, xn1 square, xn1, xn2, and xn1, xnd. Okay, I just write the last row here. The last row would be xnd, xnd, xn1. Okay, I will not write everything. And this one would be xnd squared. Okay, this is the matrix we got. And we can distribute this summation into every term here. So next time we'll not. So now I will not write everything. So I just distribute this to the first element. So this is n, right? Because we have a summation here. This is n, and this element would be xn1, and this element would be xn2. xnd here, and I will write one more. So this one would be xn1 squared. Okay, for other elements I will just leave it. I will not write everything. Okay, I will just write this one to here. So how about this? How about this one? Let's write this one. So x transpose x. So I have defined what is x. So this is our x. Okay. So what about it transpose? I just copy it so I can make it faster. So we need so here this is x and its transpose. It's just 1, and so x 1 xn1 x1d x2d xnd. So you can see if I transpose it, this column will be the feature vector of the first sample. This is the feature vector of the second sample. So if you multiply these two big matrices together, you will have this term. You will have this matrix. What is the first elements here? It's the first row multiplied with the first column here. So you will get n. So if you compare these two, so you find these two are exactly the same here. Okay, we can compare one more. If you multiply this first row with this second column, what you will get? You will get a summation n from 1 to n x n 1, right? Because only the first number is changing. So you will also find that this one is exactly the same with this one. Okay, we can compare one more. If you use this second row to multiply with the second column here, what you will get here? You will get summation from n1 to n x n1 squared. You will get this term. So you can find this term is exactly the same as this one. Okay, so for other term you can prove yourself, and it would be beneficial for your understanding. So I have proved that they are equal to each other. And how about these two? Are they equal? Okay, let's prove it. So that's here. This one is equal to x. Okay, I have proved it. How about the next one? Okay, how about this one? How about this? Okay, I will use the similar methods. So here, okay, now I write this summation. So also we expand the xn. So xn, the first entry is 1, the second entry is xn 1, because this is the n sample, xn 2 and xn d. Okay, and yn is a scalar. It's a number. It's not a vector. So also we distribute every term here. We get yn, the second one, xn1 yn, and the last one, xn d yn. So this is the vector we get. So if it's equal to x transpose y, okay, we write x transpose y. Okay, we need this x matrix, this very big matrix. We copy. Oh, so I should copy x transpose. So this is x transpose, and how about y? Y is the vector we defined, right? Y is this vector. I just copy it. Okay. So if you multiply this matrix with this vector, you will get the first one is a summation. Use this row to multiply with this column. You will get yn, so n from 1 to n. And the second one is you use this row to multiply with this column. You get xn1 yn, right? Okay, and lastly we have xnd yn. So you can compare these two vectors now. You can find these two vectors are exactly the same. So we have proved that they are equal to each other. They are equal to each other. So we have proved this one, and we have proved this one. So we can definitely write in this matrix form. Okay. So proved. Okay, this is just our proof here. Okay, we will continue with this matrix here, matrix calculation here. We will continue with this equation. Let me copy it. Okay, maybe. Okay. So because this equation is after I set the gradient, so I put a star here. Means that this is the optimal weights that we want to find. So if I write this way, everything goes to very simple. I just move the x transpose y to the right hand side. So if we want to use this one, so we will assume that this matrix is invertible. So it's invertible. We got omega star equals transpose, right? Because we will multiply with the transpose on here and on here. We will multiply the transpose, and we got this. So this is the final closed form that we want to find. for our linear regression problem. So we can observe this. What is this equation we finally got? So it means that if we have some training data, training sample, this training sample has some feature vectors. And those feature vectors will form this big matrix X. And also this training sample has some labels because we are doing supervised learning. So it has some ground truths. So all those informations on the right hand side represents the information from training points. That's it. And the training points, we know what are the training points. So we have all the informations. So we can know the right hand side. If we know the right hand side, we can just plug them in this equation, and we can finally we can finally calculate the optimal weights. That is omega star here. Okay. So this is one method. We can calculate omega star. And we have another method here. Okay. And we have another method also to calculate this omega star. And maybe this method is easier. So we will also start with this loss function because we want to minimize it. Okay, we will also start with this one. Okay, now I will do a different thing here. Or maybe put it like this. Okay, I will write this one to a matrix form. You should convince yourself that this one is equal to x omega. So this x is the matrix we just defined, and omega is the weights vector, and minus y. So we take the Euclidean distance here. So this notation means Euclidean distance. So this square means we will not take the square root. We just take the square of each element here. So this is the square of the Euclidean distance. So you should convince yourself that these two are equal to each other, because the first row of the matrix here is the feature vector of the first sample. If you use the first sample to multiply with the weights, you get the prediction of the first sample, and you minus the ground truth of the first sample. So this is the first element in the vector y. And so you get a vector here. You will have a vector in this one. And also you use the second row of this x to multiply the omega and minus its ground truth. It's when n equals to 2. So they are the same. Okay. And you can also expand everything here. I will not expand here to save some time. Okay, if we write this in a matrix form, and I can also write it in this way. I will write this one because it's a vector. I will write it to the transpose and multiply with itself. This is also easy to understand because this is the Euclidean distance. For example, if we have a very simple vector, 1, 2, its Euclidean distance is just 1 square plus 2 square. So it will equal to, I take its transpose 1, 2 and multiply with itself. So it will equal to 1, 2. So you can see these two are the same. So that's why I can write it in this way. Okay. Okay, then let's continue. So I will distribute this transpose inside of it. So I will write this one to front and multiply with this. So omega minus y. So then I will distribute everything here. And omega t x omega. And okay, I just expand everything here. Okay, let's see what are these two terms here. So we know that omega, this is a vector. This is a vector. Okay, this vector, and I take it transpose, it will be like a row vector, like this. And this big X, capital X, is a matrix. So if I multiply with these two, what I get? I will get a row vector. And if I use a row vector to multiply with this y is a column vector, I will get a scalar, just a number. So this one is just a scalar. How about this one? How about this one? So this one, y transpose. So y transpose is a row vector. And I multiply with this X matrix, I will get a row vector. And then I multiply with this weights, it's a column vector. So this one will also give me a scalar. So these two are scalar, just a number. Okay, and we can also find interesting is that this one, omega transpose, x transpose y, it is equal to this one take the transpose, right? So, and we know they are scalars. So what if I take a transpose over scalar? So it's still itself. So these two terms, so they are equal to each other. So they are equal. So we can write this equation like this. Because they are equal, I just put a 2. Because this is just a number. And I keep the y transpose y. Okay. We simplified this loss function to this term, to this equation here. And then we will use the equations I have proved here, this equation. And I will also tell you another equation is that so we will use this equation here. If I have omega transpose A omega, and we take a partial derivative over omega, it will be equal to A plus A transpose omega. Why do we need that? Because this is our loss function. Next step, we will take the gradient over omega. So it's the partial derivative of RSS omega over omega. So I will firstly take the partial derivative this omega, and this over omega, minus, I put this 2 in the front, ft, xt, y. I put a bracket here. So this one, because this y is not connected with omega, so I take a derivative over omega, it goes to 0. And we will set it to 0 here. Okay, now we will use this equation here. So we can see that this xt, x transpose, x is this A, right? And so it will give us this equation. I take a transpose because this has a transpose, and we have a omega, and we minus. So this one we have proved that why this is true. So this one will be equal to x transpose y, set it equal to 0. And so we also find that when you expand this one, it will give us t x transpose x omega minus 2 x transpose y. So this 2 is cancelled out. So we have x transpose x omega minus x transpose y to 0. So here I will put a star here. Actually, they all has a star because you have set the gradient to 0, so it will give you the optimal weights here. So we find that it is the same as before. So it's all the same now. If we just move the x transpose t to the right hand side, and then our optimal weights is x transpose x inverse x transpose y. So this is the closed form we got from the second method. So if we compare, this result is exactly the same as the first method here. And this second method seems easier. And so this is the closed form that we have. Okay, so we went through a very long mathematical calculation, and finally we got this linear regression closed form solution here. So we can have a summary here. So this is the closed form solution of linear regression. And let's see closely what are these. So x, so we define x, right? So x, matrix x, this is a very big matrix because we will have many samples, we will have many features. Matrix S is the matrix contains all the feature information. This makes sense, right? Because if you look back on how I defined x, so I define x in this one. So the first row is the feature vector of the first sample. The second row is the feature vector of the second sample. The nth row is the feature vector of the nth sample. So this very big matrix X contains all the feature vectors, contains all our training points. So this matrix is very important. And what about vector Y? we have vector y here. Vector y is the vector contains all the labels or ground truths. So you can see how I define the vector y here. This is our vector y, right? So y1 is the ground truth of the first sample, y2 is the ground truth of the second sample, and so on. Okay, if we have this information, we can calculate our weights. We can calculate our hyperplane. So lastly, theoretically, we can calculate the optimal weight vector omega star on any data. By using this solution. So this is why it is called the closed form solution, because this one we can use this solution in any data, on any data. Okay, I think we can wrap it up here. So this is our final solution for the linear regression problem, and I will also have one or two videos also on linear regression, on overfitting, underfitting, something like that. And I will cover it maybe in the next video. Okay, I will stop here. Thank you.